We are talking about the magnetic field intensity of the coaxial cable. Right? We found that magnetic field intensity exists if current I is flowing through the inner conductor. Current I is flowing through the inner conductor. Magnetic field exists inside the inner conductor. Okay, and that magnetic field has this much strength. And the magnetic field exists uh, between the two conductors, the inner conductor and the outer conductor. So the magnetic field intensity exists between the gap, in the gap H, and that magnetic field intensity is this much. We also found that the magnetic field intensity also exists inside the outer conductor here. And that magnetic field intensity also has an equation and is given here, right? We also saw that the magnetic field intensity outside the conductor is zero. There is no magnetic field intensity outside the conductor. Okay. Then we calculated the inductance. We said if the magnetic field intensity exists inside inner conductor, inside the gap, inside the outer conductor, so there's inductance inside the inner conductor, inside the gap, and inside the outer conductor. So then we calculated the inductance of the coaxial cable using these equations, and the inductance of the coaxial cable. Then we added the inductance of the inner conductor, the inductance of the gap, the inductance of the outer conductor. We added all the three inductances and calculated the total inductance of the coaxial cable, right? And then we combined this inductance of the coaxial cable with the capacitance of the coaxial cable, which we calculated previously in chapter number 6. So when we multiply the inductance of the coaxial cable and the capacitance of the coaxial cable, we end up on finding out the phase velocity of the electromagnetic wave which will flow, which will propagate through the coaxial cable. So this magnetic field, this phase velocity, 1 or Vp square will be equals to mu epsilon. From this equation, we can also suggest that Vp is equal to 3 into 1 over under root mu naught epsilon naught mu r epsilon r, which is equal to nearly equal to 3 into 10 to the power 8 meter per second, and divided by mu r epsilon r. Okay, so this thing is 3 into 10 to the power 8 divided by the refractive index of the material of the this mu r and epsilon r, or the refractive index, is of the material used between the two conductors. That white plastic sort of material which you see in the coaxial cable, that's a dielectric which you use in the coaxial cable, for example, a Teflon, right? So that's the characteristic impedance of the, this will lead us to the characteristic impedance, which we have not find out yet, but we will be able to calculate the characteristic impedance of the coaxial cable using all these terms. So importantly, the phase velocity of the electromagnetic wave which will move through the coaxial cable will be equal to 3 into 10 to the power 8 divided by the epsilon r and the mu r of the dielectric, is dielectric, right? And it's such a simple equation which is going to give you the velocity of the EM wave which is moving through the coaxial cable. Okay, now let's see briefly on the curl operator. Curl of a vector field is going to give you the loops per unit area. Okay, loops. For example, if you have this magnetic field.
Excuse me sir.
Yes, yes, yes.
सर एग्जाम पॉइंट ऑफ व्यू से सर हम इसकी सिर्फ इक्वेशंस देख लें सर, डेरिवेशन रहने दें.
uh,
कंडक्टर की?
ये जो इसकी इंडक्टेंस है,
यस सर, टोटल इंडक्टेंस निकालने तक।
हाँ, टोटल इंडक्टेंस निकालने तक I'll suggest for a while, if you know the magnetic field intensity of the coaxial cable inside inner,
ओके
inside in the gap, inside the outer, if you know this thing, and if you know how to calculate the inductance out of the magnetic field, okay, if you know how to calculate inductance out of the magnetic field, I guess that will be enough for you. And then further, at least try to find out one thing. At least try to find the inductance of at minimum inner conductor, at minimum, just to know
ओके
how you will be able to find the inductance of the gap and the inductance of the outer conductor. So at least go for one, so you
ओके
get a
सर।
better idea how to calculate this thing. The important thing is when you multiply the inductance and the capacitance, we are going to get some very interesting results, and that interesting result is about the phase velocity of the EM wave. So this is the phase velocity of EM wave. Though we have not studied yet the time varying fields. See, if this is say the z-axis, say this one is the x-axis, and say this one is the y-axis, right? So the electromagnetic wave will have electric field, for example, oscillating like this and moving in this direction. Its magnetic field will really be oscillating along y-axis. Okay, will be oscillating along y-axis. So this will be the magnetic field, this green one, oscillating along y-axis. Look, the magnetic field is maximum when the electric field is maximum at this phase, at 90-degree phase. So the speed at which the phase of the electromagnetic wave is moving forward. For example, uh, say in second number one, the phase is here, but in second number two, the wave will move a little forward and will come here. Okay, and similarly, if you draw the new electromagnetic field, it will look like this, right? Okay, so now look, this phase is moved here. So how much distance is covered? How much this distance by the phase is covered by this point? How much distance is covered in z direction? And in what time? And in what time? That will give you the phase velocity. And that phase velocity is here. So it's very interesting that we were doing we were calculating the capacitance, this one, for electrostatics. We were calculating capacitance for electrostatics, meaning the charges were static. And we were calculating this inductance for magnetostatics, meaning the current was DC. I was DC, and from I we were getting the magnetic field, and that magnetic field was called as magnetostatics, okay, from the DC current. But very interestingly, that when we multiply this inductance, which we calculated from magnetostatics, to this capacitance, which was the condition of electrostatics, when we multiply them together, we get something, some new parameter, which is the phase velocity, and that is for time varying fields. Now, this is a little bit interesting. Okay, a little interesting. So anyway, we will go through this. We will come this basically open up a new chapter for us, which is for the time varying fields. And in this week, our objective is to cover the time varying phenomena in this next one or two lectures, right? So that was a little interesting. So I hope you should understand these things and go through and try to think over a few new things which are coming in the next lecture. Okay, so we were so now we want to see a little bit about the curl operator. The curl operator, the curl means the curls, right? The loops. So whenever you try to calculate the curl operator of a vector, it's going to give you the revolutions, going to give you the loops. For example, curl, curl of a magnetic field. Okay, curl of a magnetic field. So meaning curl of a magnetic field means how many loops you have of the magnetic field in a unit area. How many loops you have the magnetic field in a unit area. This is magnetic field, this is magnetic field, this is magnetic. How many loops you have in a unit area. That is going to give you the curl. That's actually the curl operator. And just like we saw the equation of H dot dl integral, the closed loop integral, this was current I. This was the current I, if you remember, this was the Ampere's law. Ampere's law. Okay, so H dot dl. Look, if if current I is flowing through a wire, current I is flowing through wire, and say the wire is a closed wire, and then the magnetic field of it, the magnetic field around it is H, and say this is the dl, the differential length of the path H. So this is really going to give you the Ampere's law, this situation. So when we take the curl, look, this is the integral. This is the integral form. The integral form is going to give you current I, and this one is the differential form. Because look, you know that the del operator is the del operator. You remember the del operator in Cartesian coordinate system. The del operator is partial by partial x in the direction x plus partial by partial y in the direction y plus partial by partial z in the direction z. So the del operator is the space parameter, going to give you the space variations, the variation for something in the space. So this curl of H is going to give you J, the current density, which is I divided by area. Okay, so number of loops per unit area, revolutions or per unit area is the curl operator. It's the so the unit of the curl operator is revolutions per unit area. Remember, okay. So this is going to give you the current, the J parameter. We're going to give you the J parameter, J. Okay, going to give you the J parameter. So the curl operator in the curl of a vector F, curl of a vector F in Cartesian coordinate system, in Cartesian coordinate system is this much. Okay, and how you calculate the curl of a vector? Curl of a vector, how you would do that? You go through the determinant of a matrix method. So you first draw the unit vectors. You first put the unit vector in the first column, and in the second column, you put the components of the del operator. Components of the del operator. In the third row, you put the components of the F vector. Okay, components of the F vector. Just like with any other A cross B, A cross B vector, A cross B. How you calculate the A cross B? A cross B is the unit vector X, the unit vector Y, the unit vector Z. For example, if you are solving in the Cartesian coordinate system, and then the components of AX, AY, and AZ, the components of A vector, and then the components of the B vector. Okay, so this is how you do that. So that was a little bit about the curl operator. The curl operator in the cylindrical coordinate system, and the curl operator in the spherical coordinate system. Okay. Okay. So this was the curl operator definition, right? So the differential form of the Ampere's law is basically curl of H equals to J. So that's the differential form of the Ampere's law. The integral form of the Ampere's law is H dot dl. integral equals to current I. Okay, so the differential form of the Ampere's law is, if this is the if this is the curls, okay, curls of if the magnetic field is going to be in this direction, okay, so you have h of x, surely it will have three components, the x, the y, and the z component. So curl of h is going to give you j. Okay, curl of h is going to give you j, and j will have the three components, jx, jy, and jz. Any question here? Any question here?
No, sir.
Okay, so these are the few equations. Remember, you went through the first Maxwell equation. The first Maxwell equation was divergence D equals to rho V. You remember that equation, divergence D equals to
Yes,
rho.
sir.
That was the first Maxwell equation. So we are coming back to the first Maxwell equation, and let's see what we can find a new thing. There's another law called as the Stokes theorem. The Stokes theorem is going to give you a closed loop line integral, a closed loop, a closed loop, closed path integral. Look, h dot dl is closed path. You remember E dot dl integral was voltage AB. Okay, you remember that, a closed loop, and it was zero in the closed loop. The voltage drop and the voltage rise, they all goes to zero in the DC case. Okay, so this equals to current high. H dot dl equals to current I. E dot dl equals to voltage, but in closed path it must be zero. Okay, in the DC case. So this is the dl, this is the closed path integral. Okay, so when you have a vector and a closed path, then by Stokes theorem you can transform this into curl of f dot ds. Curl of f dot ds. That's in the Stokes theorem. Okay. So transform this line integral into surface integral. So this is the surface integral, this one, right? This is a single integral here. Here we have double integral or the surface integral. Okay, surface integral, the double integral. You have two-dimensional integral here, single dimension. So so really you can transform things this way. There was another law, if you remember, that was the divergence theorem. In the divergence theorem, you are transforming the surface integral into volume integral. Okay, or you in the reverse, you can reduce the volume integral into surface integral. Here from surface integral, you can reduce down things into line integral using the Stokes theorem. So these are the two theorems which will help you a lot in simplifying the equations in some advanced courses. If you use this Stokes theorem, you can really find a new thing, and that new law is the second Maxwell equation. Okay, so see, just like with the integral d dot ds equals to how much? It was psi, the electric lines of forces or the charges q enclosed, right? D dot ds. So what should be the b dot ds? The magnetic. See, this was the electric flux density. The electric flux density dot ds, this is what? This is Gauss's law, if you remember. So B dot ds is how much? It should be magnetic flux, phi, and should be equals to magnetic charge. And remember, there's no magnetic charge in this universe. It's zero. Okay, so B dot ds is equal to zero. Okay, remember d dot ds, the electric case was equal to psi, which was equals to q enclosed. So the counterpart in the magnetism is b dot ds, which is coming out as zero. Okay, so b dot ds is 0. And B dot ds is, B is mu H dot ds equals to 0. Okay. So if you apply the divergence theorem, look from the previous page, this was the divergence theorem, this one. This is the divergence theorem. So if you apply the divergence theorem, say F is replaced with B, here you will get B. Okay. So let we replace F with B in the divergence theorem. What we are going to get, B dot ds equals to divergence of B, this thing equals to 0. This thing is 0. So this ultimately means divergence of B, because volume integral is something is not 0, there is a volume, but that also means if the left hand side is 0, that means the divergence of B is 0. So that's the second Maxwell equation. You remember a very similar equation, divergence D. How much was divergence D?
Rho v.
Rho V. That was what? That was the first Maxwell equation. Okay, it was the first Maxwell. You can make another analogy here. You can make another analogy. What is the first Maxwell equation? Divergence D equals to rho V, which equals to electric charge divided by volume. So what is the counterpart in magnetism? Similar law in magnetism. Divergence B equals to magnetic volume charge density, right? Which equals to magnetic charge divided by volume. And you know there is no magnetic charge. Magnetic charge is 0. So divergence B is 0. That's the second Maxwell equation. Okay. If you somehow you discovered a magnetic point charge, because by this time scientists are not known to magnetic charge. For scientists, this thing is 0. There is no magnetic charge in this universe because it's not discovered. Okay, because it's not there right now. But maybe if you discover this, so you will prove this wrong. The second Maxwell equation, probably you will find many new phenomena. But for a while, to this point, the the assumption of zero magnetic charge in this universe is working. Okay. Let's make some talk on the magnetic materials. The magnetic materials, B equals to mu H, and this is magnetic flux density, magnetic electric field intensity. This is intensity, magnetic intensity, magnetic field intensity. This is magnetic flux density. Okay, so B is equals to mu naught mu R H. Okay, B equals to mu R mu naught H, and just like with the electric fields, this mu R is really 1 plus zeta and magnetic susceptibility. Previously we had the electric susceptibility, now we have the magnetic susceptibility, right? So we have magnetic susceptibility, right? Previously we had the electric susceptibility, now we have the magnetic susceptibility. This zeta m is the magnetic susceptibility. By magnetic susceptibility, we means how much the material will favor the external magnetism. Okay. This zeta m is magnetic susceptibility. Zeta m is the magnetic susceptibility. Okay, it's just a reciprocal. It is reciprocal of uh, uh, look, I would say reactivity, right? I would say reactivity, but see, how much I'm correct, it's just really depend on your previous knowledge, right? Remember, there was the reactance. You remember that the reciprocal of the reactance is susceptance. Okay, the reciprocal of the reactance was susceptance. Okay, reactance was something a very bad thing. Remember, you know that, and the reactance was really coming from the impedance. Impedance was the resistance plus minus reactance, if you remember. Inductive reactance was taken positive, capacitive reactance was taken most negative in those previous mathematics. Okay, reactance is really, for example, if I have this little circuit, right, and suppose this is the resistance here, R, and this is V. So how much current I will flow through my circuit? I will be really equals to V divided by R. Okay, V divided by R. And see, if my voltage is of this shape, V divided by R, right? Okay, now if somehow in this circuit I have a reactance part, L also, so then my current I is plus J XL. That XL, J XL equals to, or XL equals to 2 pi FL. It's the reactance. That reactance is coming from inductance. The effect of that is reducing current I. The effect of this reactance is to reduce the current I. Okay? Or if I talk about the power, so power is V into I. So it really means, if I draw the diagram, this is this horizontal line is P equals to VI, the real line, the real power. This equals to sorry, horizontal line is, this power is VI. Okay, this horizontal line is VI cos of theta. Okay, if this is say the theta, or if I go, if say this is my R, this is XL. Okay, so this is the power given, power, the apparent power, P apparent. Typically we denote P apparent with S. Okay, the apparent power is part of the apparent power is going into inductance. So basically what happens, if you have some reactance in the circuit, it will hide some power from the real resistance. It will reduce down the power for the real resistance or for the real load, right? And some power will go through the imaginary part of the load during the positive half cycle. During the negative half cycle, that excessive power will be given back, to the load. So this reactance is going to deceive you. It hides power from the circuit. It hides power from real resistance, which is actually equals to I square R, which is actually the heat, which is the real power, which will do the real work. So by having reactance in the circuit, it will lower down the available power for the resistance, which is reality, which is real thing, in the first half cycle, in the positive half cycle. In the negative half cycle, in this negative half cycle, what happens? That hidden power, which was momentarily stored in the magnetic field of this inductance, this inductor, which was momentarily stored in the magnetic field of this inductor, it is released back towards the source. अब सोर्स उस पावर का क्या करेगा? टाइम तो गुजर गया, वो इंस्टेंट जहां पे उसने सोर्स ने पावर जनरेट की थी पहले हाफ साइकिल में, इस वो इंस्टेंस तो गुजर गया, उसने लोड की तरफ पावर भिजवा दिया था, लेकिन उसका कुछ हिस्सा इंडक्टर ने छुपा लिया अपने पास मैग्नेटिक फील्ड में और अगले हाफ साइकिल में वापस सोर्स की तरफ भिजवा दिया। सो सोर्स के लिए तो अभी वेस्ट है। सो सो रिएक्टेंस इज अ बैड थिंग if you consider it very generally. Sometimes we take advantage from this concept, but reactance is really a bad thing. It is a good thing if you are looking for the induction phenomena, but reactance is a bad thing overall. And this will really make a factor called as power factor, which equals to cos of theta, which is the angle of this thing. The cos of this theta is the power factor. Okay, so it's a bad thing. And the reciprocal of the reactance is a susceptance. So meaning susceptance is a good thing. It's going to help you the utilization of the power. Okay, so susceptance is a favorable parameter. So just like with resistance, we have resistivity. Just like with conductance, we have conductivity. With reactance, we have possibly reactivity. Okay, so with susceptance, we have the susceptibility terms, but we define this susceptibility terms for magnetic field and the magnetic susceptibility. And it's really modeling this mu r. So magnetic susceptibility is how much the material will favor magnetic fields, how much the material will boost the magnetic fields, how much the material will strengthen the magnetic fields, how much magnetism will be created in those materials is really depending on the magnetic susceptibility. So it's a very favorable term for magnetism, magnetic susceptibility. Okay, so we will see um, uh, some of its um, effects on materials, right? So so if you have a diamagnetic material and say some external magnetic field is here. If you have a magnetic material, some external magnetic field. See, if mu r is low, yeah, yes. अभी तक नहीं आया, शायद deep पे. If so, the magnetic susceptibility is, if it's very low, then it really means the material is not going to accept the magnetic fields. It's really not going to collect the magnetic fields from the external source or from the external environment. So if you try to pass a magnetic field through a material, the material is not going to accept that. Why? Because its magnetic susceptibility is very low. If I go for a paramagnetic materials, another class of magnetic materials, where again in the paramagnetic materials, mu r is little bit higher, and the magnetic susceptibility is little bit higher than the diamagnetic materials. So what they do, if you allow magnetic fields through it, they will try to collect some of its fields line and will allow them to pass through, thereby little bit favoring the magnetism. So paramagnetic materials, though very, very weak magnets, but they little bit they favor the magnetic fields. Okay, and why we call them paramagnetic? Because as I said previously, we have electron clouds where the electrons are moving with tremendous speed. And from the right hand rule, if the finger is going to give you the direction of the magnetic fields, the thumb will give you its magnetic moment. So these are the magnetic moments. These arrows are the magnetic moments. In the paramagnetic material, these magnetic moments are very random. You can see they are all over the place. They are in every possible direction. So such materials are very, very weak magnetic materials. But they very subtly, they very minutely, they very at minimum, they favors the external field. And if you apply the external field to them, this magnetic moment, this one, it will try to little bit to reorient. It will try a little instead going in this direction originally, it will try to make a path like a little bit in this way. Similarly, this will little bit try to come down. It will try to come down just